The babysitter was bicycle for 25 years. And he says that's because his bicycle never been stolen.
The Swedish things are just very social.
I saw your astronaut outfit.
I was planning to bring my
I was
food
in
here,
Houston, I almost got
but
my
then the
Goddard
meeting
one.
ended
It
somewhere
was
5
like
minutes ago, and
size 1, but then it had a big
I'll
label
starve
that
and
says,
eat later.
you know, small parts not suitable for children under 3.
So
And
I'm
like big massive.
But now I'm really Jewish now, and I have no money with me.
Just the
And
fries.
this one I made myself, so I bought a... You can use the money later coveralls. No, I don't want to put the sticker on. I have my badge, my GISS badge. I made an American flag, so it's excellent.
Okay.
The first part is
Should we go?
the olden part you have to go. They say some, they repeat most of the things that are from
Okay. Tell us
they really know
about your research.
Hi everybody. Okay, I'm relatively new here. I've been here for 3 months so far, and I'm new postdoc for Jerusalem. I did my PhD at Carnegie Mellon University with Dr. Peter Adams, and my research was focused on aerosol modeling, especially aerosol indirect effect, which I will talk today. And I did many different work, but today I will focus on 2 topics: the impacts of nucleation on cloud like property and cloud albedo forcing, and also impacts of black carbon mitigation on aerosol indirect forcing. Aerosol has important impacts on climate. They can scatter or absorb the sunlight, which is called a drag effect, but they can also form the cloud droplet by acting as a cloud condensation nuclei. This is called aerosol indirect effect. So this image is showing you a drag effect. This is a dust storm from the Africa. This is to show you indirect effect. This is a ship track, the cloud formation along the ship track. So from now on, I will use GCM for the cloud condensation nuclei. So a little more about aerosol indirect effect. It can be divided into 2 effects. So we call one is enhancing cloud brightness. The second is modify the precipitation efficiency. How the aerosol can have that kind of effect? Basically, when there is a high aerosol number concentration, and there will be more cloud droplet will form. Assuming liquid water content in both clouds are same, then the same amount of liquid water would distribute to more cloud drop, therefore their size will be smaller. So more cloud drop, but smaller size is more effective to reflect the sunlight. And this is called the first indirect effect or cloud albedo effect. So when the cloud size is small, it takes a longer time to grow to bigger drops, because a small particle is not efficient to coagulate each other, and it just needs a longer time to form the bigger drop. And it can modify the precipitation efficiency, and that's called the cloud lifetime effect, or second indirect effect. So IPCC first assessment reports come up with the best guess for radiative forcing for individual climate agent, including aerosol. But in this figure, what I want to focus is in this arrow bar. So in fact, this bar representing the 90% confidence interval. Basically, large bar means there is less confidence on this estimation. So as you can see, that aerosol indirect effect has a large bar, and that also affects this large bar in total net human activity. So improving our understanding on aerosol indirect effect is very important to improve our understanding on net human activity. So, and also I'd like to mention that cloud lifetime effect is not included in here, as it's highly uncertain. It's even more difficult to estimate.
Yes. I just want to make one comment.
Yes.
That the uncertainty on the CO2 is too big.
Mm-hmm. In this
Yeah, the IPCC overestimates the uncertainty because they throw in every model that participates.
I see.
If you you look at the spread between the models that are do line-by-line calculations, they all agree much more tightly than that spread.
Got it.
So
I see.
it's even
It's
more
even more.
different than you're saying.
I see. Thank you. So, a lot of this there's many things contributing large uncertainty in aerosol inject effect, but some of them actually due to the difficulty in CCN number prediction. And I want to show you what controlling the CCN number prediction. So CCN, not all particles can be CCN. So the size and chemical information is important. So it should be large enough, and it should be big enough, and also it should contain certain amount of soluble material such as sulfate or organic matter to be activated, to form the cloud drop. So generally speaking, CCN is like a particle larger than 100 nanometer. We can say it's a CCN. So all atmospheric particles either emitted directly from source, or they can formed in atmosphere from the condensing, like low vapor pressure, like a condensing, vapor. And they can grow by coagulation or condensation. Mostly is by the condensation. And all particles can be moved by the deposition and coagulation. And so I want to point out that for the CCN, this is like the microphysical growth of a small particle. This has a significant impact on CCN than emission. So it's very important to have an accurate microphysics to predict this growth rate for the CCN number prediction. So this slide could be a little bit overwhelming because I put many things in this slide. The first thing I want to show you is what kind of work I did for my PhD. So I will show what kind of work I did, but also this is kind of modeling tool I used to study aerosol inject effect. So you can see the two things from this slide. So first the work I did was to develop the mineral dust model for our aerosol model, because previously it has a carbonaceous aerosol, has a sulfate, sisal, but it doesn't have a mineral dust. So mineral dust is not that important for, let's say, CCN, because they are not that active. But they are important for drag effects. They are efficiently scatter or absorb the sunlight. So we need the mineral dust to use this model for aerosol impact on climate. So that was my first work. And then since we have all the important aerosol, I evaluate our model with the remote sensing data, including MODIS, MITRE, and Aeronet. And then I did a little bit different work. So our my aerosol model predict the aerosol size distribution. It takes big time to calculate the size distribution. So it's good for microphysics, but it's bad for computing time because it's very slow. So one of the work I did, one of my main work is developing faster version of aerosol model. Try to minimize the microphysical error. So I will talk about that a little bit about that. And then I'm working on another topic, but I will just skip this one because I will not talk about that. So we have an aerosol model, but I also need cloud microphysics model to compute the cloud microphysics property as a function of aerosol. Because once in GCM is not a function of aerosol, so we need another parameterization to account for the cloud property as a function of aerosol. So I implement the new cloud models into the our model, and then I was able to answer, doing some interesting study. So first study I did was the impacts of nucleation on cloud microphysical property, and aerosol inject forcing. And then I also do one study, basically the impacts of black carbon mitigation on aerosol inject forcing. And I will talk about that more detail later. But for now, let me talk about modeling tool I use. So our aerosol microphysics model is coupled with GCM II', which is the older version of GCM. And it has important aerosol, and our scheme is called TwO-Moment Aerosol Sectional algorithm called TOMAS, and it tracks total numbers and mass for each size bin. Mass for each species, aerosol species. So we track the sulfate, sisal, carbonaceous, dust separately. And this model has 30 bin segregated by dry mass per particle, and has important microphysics process. So basically, from this model, from TOMAS model, I can get like size distribution looks like this. So each size bin tracks the total number and mass for each species. So this is what I will get. But as
the number of sizes, but the axis says 10 nanometers on,
Oh, yes.
micrometers on the other side. Okay, sorry, I see now.
okay, yeah. So actually, that's good.
It's my bad eyesight.
This is good. I have to point out this. So older version of the TOMAS covers from 10 nanometer to 10 nanometer to 10 micrometer. But one of the work I did, which I will not talk about it, but I have to extend to 3 nanometer to have a better representation for nucleation. So thank you for pointing that out. Yeah. That is the okay, so as I said, I developed like a faster version of the TOMAS. How I did it, basically simply reducing size resolution. So, but it's not that easy as I said, because I have to develop new microphysics scheme for like a course version. But so basically, like older model has a 10 bin for each. Basically, I will pick this one as an example. From 1 nanometer to 10 nanometer, older version has a 10 size bin. So basically, how we define size bin is using dry mass per particle, single particle mass. So let's say the initial size bin, size boundary is m naught, and the second size bin is 2 times of m naught, and then next is 2 times of a previous. So it's a mass doubling. But for the faster version, it's a mass quadrupling. So it's basically I'm lumping these 2 size bin together and say this is 1. But I did further. I made like a more faster version. It's called faster TOMAS, TOMAS 12 bin version. Basically, it's like a 15, 12 identical from 10 nanometer to 100 nanometer. 1 micrometer. But 12 bin only have a 2 size bin for the coarse mode instead of 5 bin. The reason is that the coarse mode don't need expensive microphysics, because their microphysics change is very slow compared to small particle. So basically, making these two faster version of model only introduce like a few percent error by the microphysics, coagulation, condensation. So we was very satisfied with these 2 models, and this 2 model is almost identical. So we actually using this model for
How was the original number of 30 bins chosen?
because well, how can I say? It is for the coagulation. So basically, when you have a mass doubling, the coagulation scheme is much simpler. Basically, the coagulation within this size bin always have to grow next to it. But when you have I can say more than double, like a size boundary, there is a coagulation inside of the bin. They can stay in here, but sometimes they can also go larger. So I have to account for that. So the coagulation scheme is a little longer or a little complicated than before. So this is how much time I can save by using faster TOMAS. So all the model, I know it's like you were surprised, but it nearly takes 2 months to simulate 1 year simulation.
You're using an Origin 2000. That machine's like 15
Exactly.
years old.
Yes, yes, that's a good one. That's right.
I could do it on my laptop.
Yeah, we didn't have enough money to buy a fancy machine, so we have to wait 2 months to get 1 year.
That's okay. We got one in the basement here. You can use that.
So then with the faster version, basically like reducing half is like 2 times faster, and 12 bin is 3 times faster. So we are actually very happy that now we don't need to wait 2 months. Okay, so that's for the aerosol model. But as I said, I introduced new cloud model, and I want to talk about that a little bit. But before that, let's thinking about cloud formation. So we know that cloud form when relative humidity is over, like 100%, it's saturated. Then excessive water vapors start to condense on aerosol. That's why we can see the cloud, the cloud droplet is forming. So basically, when relative humidity reaching, like 100%, that's the time the cloud droplets start to form. Okay, I have to say this. So there's 2 processes controlling relative humidity. The one is cooling rate, and the other is condensation. Basically, cooling is, the temperature in the parcel got cooled as it got uplifted. So relative humidity is higher as it got uplifted. But then if there's aerosol, the excessive water vapor condense on aerosol and relative humidity will decrease. So this is 2 competing process. So as long as the cooling rate is higher than condensation, relative humidity will keep increase and increase until they are equal, their rate is the same, and then relative humidity reaches the maximum, and then we call this point as maximum supersaturation. So activation is happening in this region. So basically, calculating cloud droplet number concentration is very, very difficult because this process is not linear. You cannot using simple, empirical relationship to get the cloud droplet number concentration. So we need to use more physical-based, model to account for this activation. So I'm using activation parameterization that's developed by Dr. Nennes and Seinfeld, and basically they solving equation to get the maximum supersaturation numerically. So there is a certain input they need, like a pressure, temperature, objective velocity, which will affect determine cooling rate, relative humidity, and aerosol information. So the output from this parameterization is basically the number concentration, like CD and C, and the maximum supersaturation. And how they do it is, we know that this will be maximum supersaturation occur when these 2 processes is equal. But solving this equation is not that easy. Actually, it's quite difficult. So, but they come up with a new idea that it's called population splitting. So they divide the CCN group into 2 different. One is called kinetically limited CCN. The other is recently activated CCN. So the condensation rate for these 2 groups is different. But I'm not going to explain how they do. But anyway, so having this, introducing this technique in here, they're now able to solve the maximum supersaturation numerically. So this is pretty much done. So basically, let me put everything together and see how I actually calculate the cloud, aerosol inject effect. So I have aerosol model, which I will call faster TOMAS, and it covers from 3 nanometer to 10 nanometer. It predicts the aerosol size information, and we can get the CCN information from this model. Now I have a cloud model that can compute the CD and C, which is a function of particle size. So if I have a present-day CD and C and pre-industrial CD and C, I can estimate the cloud albedo effect. for the cloud lifetime effect, if I have auto conversion parameterization, which is a function of a CD and C, then I can compute the cloud lifetime effect. But I'm not going to do this part because I don't allow any feedback to GCM. So the liquid water content is not changed, and actually like it's not that meaningful what I did, but I mean at least for this part. But there's at least one, one thing I want to point out. So auto conversion is the one to do the cloud lifetime effect, you changing auto conversion, which is you changing CDNC, then auto conversion will be changing. But I mean I'm listing many auto conversion. Auto conversion is a very uncertain process. So I will show you the equation. They look a little bit like, oh, too much. And and they, yeah, simple for you. Anyway, so and their dependency, some auto conversion is only function of the liquid water content. Some auto conversions are function of the liquid water content and CDNC. Some are more, there is more dependency. So, but if I don't change any climate but only CDNC, then simply I can list it at, this parameterization is not a function of CDNC, but this is a function of the CDNC. But their dependency, as you can see, is very different. So, so that's the one thing I want to point out. Auto conversion is very uncertain, and you can add uncertainty on cloud lifetime effect. But I'm not going to talk about auto conversion much in this talk. So we will do more interesting, talk now. So what is the impacts of nucleation on aerosol indirect forcing? Then why we have to care about nucleation? Because nucleation is very uncertain. I mean, there are several proposed mechanisms. Binary, basically using sulfuric acid and water, and we can estimate the prediction, like a nucleation rate. There is another mechanism called ternary. Now there's additional, species like ammonia is contributing, affecting nucleation rate. There is called like ion-induced nucleation. But this nucleation prediction from, nucleation rate prediction from this mechanism varied by like several orders of magnitude. They are very different. Then the question is, okay, what's the, how this uncertainty in nucleation affects on CDNC and aerosol inject forcing? But before cloud, I want to show you how do they different in the model. So I want to point out this is a zonal average plot, and the x-axis is latitude. So this is equator, this is a northern hemisphere, southern hemisphere, and this is a pressure. Basically, this is a surface, and this is like increasing altitude. So this is nucleation rate by binary, and this is by ternary. You can see they look very different. They are very different. So global average nucleation rate differ by 6 orders of magnitude. And you can see that, binary nucleation, they show some nucleation over, like a high upper troposphere, while ternary showing just throughout the troposphere, there's a high nucleation rate. One major difference is maybe problem 2. Like a binary doesn't give any nucleation near the surface, and that's a problem. They can, there is nucleation that they cannot capture. While the ternary nucleation, there is nucleation, but the one of the criticism for ternary nucleation is they predict too much. It's not realistic. So, but anyway, these are the proposed mechanism, but I want to show you.
So this was for present day conditions, or?
These are present day condition.
So the difference in the hemispheres is the amount of SO or?
Both has the same primary emission. So only difference is like nucleation scheme.
The northern hemisphere has larger values because of.
Yes, because there's more, like a certain, there is like a SO2 emission, and So,
So
but
where do you take the ammonia from for the ternary nucleation?
where did I take it?
The ammonia.
Why do
we
you
have
it in there?
Yeah, we have ammonia in the model.
We have
Yeah.
a nitrate cycle.
Yes.
Oh.
Yeah. I mean, it's not that simple, but we actually added like simple one for this ternary nucleation. But now you will see interesting, things. So this is to show the importance of simulating particle growth by microphysics. So we see it was like huge difference in nucleation rate. For now, for CN10, so the CN10 means number concentration of a particle greater than 10 nanometer. So basically, for nucleation rate predicts like a particle formation, and this particle is like about 1 nanometer. But now we're talking about particle number concentration, which their size is greater than 10 nanometer. So this small particle should grow to make it to 10 nanometer. But what I want to show you is not all particle grow make it to 10 nanometer. Especially now, so this is 2 difference. Now it's a factor of 2. If we look at the CCN number concentration, which is about particle larger than 100 nanometer is a CCN, like 0.2%. So now you can see that they all look very same, and they only differ by 10%. So huge difference in nucleation doesn't affect too much on the CCN, 0.2%. Why is that? Because as you have more particle, there is like competition for condensation and growth. We have limited amount of condensing vapor. Sulfuric acid is not a lot, so they are limited. But this has to go more particle for ternary nucleation. So less particle, there's less chance for ternary nucleated particle make it to the CN10. But still, there's a lot of particle they make it to the CN10. But the chance is very low. And another thing is when you have a very high number concentration, coagulation sink is increased. So there's 2 effects. Like you slow down growth, but also you enhance the sink rate. So that's why they are almost like looks identical. But then question is, okay, then how this will affect on cloud? Do we have the same result or different result? And I will show how today.
Yunha,
Yes.
what is your assumption from moving to from 1 nanometer particles to 10 nanometers?
I'm using microphysics. What do you
But
mean?
you said that your size bins start from 10 nanometers.
Oh, okay, that's a good point. So, do you remember? Like I skipped one of the parts, like nucleation mode dynamics.
Yeah.
Basically, one of my study was looking. So I compare explicit microphysics for 1 nanometer to 10 nanometer, and then of course 10 nanometer to 10 micron. There's TOMAS. So I changed TOMAS lower size bin, like size boundary from 10 nanometer to 1 nanometer, and also 10 nanometer to 3 nanometer, and then compare how do they do. So original TOMAS, they don't have explicit microphysics for nucleation mode, but they do using parameterization. So there is a parameterization developed by like Camino et al. And basically you account for the condensation sink, you account for coagulation, and they come up with the parameterization. So you don't need to fully simulating nucleation mode to account for the growth. Am I?
Yeah, sure. That's
Okay,
fine.
yeah. So we do account, but the way we account is a little different. So, okay. So to answer the impacts of nucleation on aerosol inject forcing, I have 4 different simulation. Basically, 2 for binary and 2 for ternary, because each one has a present-day emission and pre-industrial emission. So using these 2 simulation, I can have a cloud albedo forcing based on binary, and this is like cloud albedo forcing based on ternary. So I will see how using different nucleation show the different result for the cloud albedo forcing. And so this is the first vertical layer CDSC change from pre-industrial to present day. So we expect that CDSC will increase because we have much more primary emission in present day. So, okay, don't look over 45 and north, but just looking below, they look pretty similar. There is a difference, but overall, there's some peaks in continental region where it has high primary emission. There is some peaks similar, but there is a difference. For example, so using binary, using ternary, there is a less CDSC increase over the continental region, which is interesting. But the reason actually is more like a simple reason. Basically, pre-industrial has a less primary emission, as you expect. But when you have a less primary emission, there's not much aerosol around. So when you have a nucleated particle, they are not going to, coagulate with the existing particle. So they can stay longer, and they have a higher chance to grow to bigger. So present pre-industrial with the ternary actually produce quite a bit high the CDNC. So the changes in CDNC from pre-industrial to present day, ternary is less than primary, like a binary, because as I said, pre-industrial CDNC is much higher than when we use a binary. But the same logic applies to the southern hemisphere, but the result, the sign is opposite. So basically, the result is opposite. So when we're using ternary nucleation, there is more CDNC increase than binary. Again, similarly, we know that southern hemisphere, there's less primary emission compared to northern hemisphere. So the nucleation has a higher chance to grow. So having higher nucleation, you will have a higher CDNC in this region, which is consistent with what other the model found. But okay, now we talk about this issue. I don't have a good answer for this. This is rather interesting. So ternary nucleation actually giving interesting result. CDNC in present day actually less than CDNC in pre-industrial. So if I'm using microphysics, and try to explain, I may say, yeah, maybe there's a growth rate in present day maybe slower than pre-industrial, because there's so many particles and there's less sulfuric acid to grow. So their growth is maybe less than pre-industrial. But another thing I found is that when I compute the CDNC with annual average aerosol fill or monthly average aerosol fill, actually I got higher CDNC for present day than pre-industrial. So there is a difference when I'm using offline CDNC calculation versus the online CDNC. This is online CDNC calculation. Their result is the opposite. And I'm not sure how to explain this issue. So it's it could be both is contributing there, but if you have a comment on this, I will happy to hear. So anyway, so that's for the CDNC, and you can see that their regional impact is very different. So for the cloud albedo forcing, it's kind of a correlate with the CDNC change. So overall, there is some similarity between two, but as we expect, since CDNC in present day is lower, so this is a warming effect. There's a warming effect there, and therefore these two global average forcing numbers are quite different, and this is not consistent with the other global model. And
Yunha, you did that. That's not interactive, right?
yes, and sometimes, cloud albedo forcing, I can say, some model.
That's why it looks so beautiful,
Yeah,
Otherwise
exactly.
it looks very
Exactly, that's the truth. And the reason I didn't allow any feedback, I didn't changing any cloud. So basically, you know, these two meteorology is identical. So only change is like primary emission and nucleation rate. And the reason is that we cannot do, still with the faster TOMAS, it's hard to do like 10-year simulation because it will take 1 year to complete. So yeah, so we actually using like identical meteorology. Okay, so from that, unlike CCN, we actually think that aerosols inject first thing in the region is quite sensitive to the nucleation scheme. And okay, so actually I will skip this order conversion. Okay, then let me talk about the black carbon mitigation. This is interesting, and this is a collaboration with like Caltech people like John Seinfeld and also Dr. Nanas in Georgia Tech. And our paper is published in GRL this year. So black carbon is interesting than compared to other aerosols. The reason is they can absorb like solar radiation. And because of that, characteristic, they can, like contributing positive warming. They can contributing warming, but also when the black carbon is in the cloud, they can change in relative humidity, basically let the cloud droplet to evaporate. And also when black carbon is spread over the ice surface, they make the surface darker, so the albedo will be reduced. So these are all, the things I listed here is all contributing to warming. So and so far people has been focused on this one a lot, but then our studies, so what about cooling effect? We think, black carbon by itself, they are not going to activate. But if a black carbon is internally mixing with, like, let's say sulfate, then they can activate. So, reducing black carbon can actually, affect on aerosol interact effect if they are, internally mixing with other soluble material. And also, when you reduce black carbon emission, it's hard to just reducing black carbon because black carbon is emitted together with the organic carbon or sometimes sulfate. So when you cut down black carbon emission, you can also cut down the other soluble material, which is important for CCN number. So our study, we have 3 simulations. One is a base case, there's no mitigation. And the one simulation, we have a 50% mitigation for the fossil fuel emission. And also the other is all carbonaceous emission we reduce by 50%. And the carbonaceous emission has 3 kinds in the global model. So one is a fossil fuel, biomass burning, and biofuel. And this is to show, so how we treat this in the model is very important, how we treat this primary emission. So for the fossil fuel, fossil fuel has a high, it has a high fraction for the black carbon. EC is black carbon. And biofuel and biomass burning, there is less black carbon than fossil fuel. So, and the fossil fuel tend to have a very small size than the biomass burning. So this is for the fossil fuel and this is for the biomass burning. But you can see that their mass is much higher than fossil fuel. But in terms of number, actually fossil fuel has a big contribution of number since they are much smaller than biomass burning. So as I said, I have a 50% reduction for fossil fuel, 50% reduction for all this emission. So this is the result. So I'm showing you for the fossil fuel only. So this is a CDNC reduction by the CDNC reduction when we cut down 50% emission for fossil fuel, you can see there's overall decrease, and this decrease is about 5% in global average. So, which means that you will actually, how can I say, indirect forcing will be reduced since you have a less CDNC. So, what people has been, so when people propose for the black carbon mitigation, they've been focused on this warming effect by the, what is it, this is a snow ice darkening, cloud burn-up, this is semi-drag effect, and this is like a drag effect by black carbon. So looking this, if you reduce the 50%, you actually, you will have a cooling effect. But if you account for the indirect forcing, you will actually have some warming. So overall, you may have warming, but you are not going to see, I can say, much warming than what people propose because they didn't consider indirect forcing by the black carbon. Okay, actually that's all I want to say, and this is just one thing the take-home point for you guys, and I will just stop here, and I'm happy to take in any questions.
Does the black carbon get to change the thermodynamic profile of the atmosphere?
They do, but not in our model. I have to actually, I have to tell you that this is what we simulate. This is not my work. The indirect forcing calculation is done at Caltech. They're using GCM III, which is a little better than what I have, but maybe not as good as Model E, perhaps. But anyway, but we didn't have this component. So this is not from our model. So this is semi-drag effect, or this is basically we look at the reference and come up with, you choose best guess and do kind of simple adjustment for the 50% and come up with value. But in the model we don't have semi-drag effects.
And the cert doesn't nucleate ice.
Sorry?
Does the cert nucleate ice?
By itself, no. But generally, they actually existing with other soluble material. They are not totally by itself. Near the source, yes, but not generally. Further from source, they coagulate with sulfate or coagulate with organic carbon. So there's some soluble material, and they can activate once they have some soluble material. No?
Well, then they'll activate water clouds once they've got soluble material, but before they have soluble material, they can act as ice nuclei.
Yeah, they can do ice nucleation.
And then they have a different
Right.
effect on clouds.
So this one is not, it's only
just
for
liquid
warm
clouds.
cloud. It's not for ice cloud. Yes.
Internally mixed, you mean homogeneously internally mixed, or you take into account the core shell structures?
Well, so in terms of a CCN, actually, how can I say? Structure, I think, is not matter. For radiation, it is.
It would matter because if you have only soluble material from the outside, then you can say that about water absorption, it's only sulfate, for example, and there is no black carbon.
Well, so based on previous studies, they actually show that mixing state, as long as there's some aerosols, I can say soluble material, in terms of activation, it doesn't matter. They can activate. So I don't know if there's some other study they show difference. I'd like to see.
No, I'm just asking.
Yeah. But generally, it doesn't matter. Radiation it matters. Yes.
Yeah, this is only the argument I have when I discuss this with people is mixing. I also agree mixing state doesn't matter for activation.
Yes.
But mixing state matters for number concentration.
Well, I want to say so when I say
because I think there was this big paper out in Science or something a few years ago where they were only size
is a matter. Yes.
Size matters, yeah.
So
I know
but they always forget the whole story before that. How do you get to your cloud droplet number concentration in there, mixing state matters. So.
Yeah, so I will clarify a little bit. So we don't assume they are all internally mixed. So when I say like like I said, within the size bin, we assume they are internally mixed, but their chemical composition is different to the other size bin. So it's like internally mixing for one size, but not for the other. So
yeah, of course. Otherwise, you have only one size.
No. I'm not. That's a little bit different point.
No, if you have different size bins, then they cannot be internally mixed by themselves. They have different size bins by definition. Yeah.
I mean, sometimes people confuse, like when I say internally mixing, they think like, oh, the whole particle is like same composition, but it's not. Yeah. So.
No, it's just internal mixture means that you consider several components in one particle.
Yeah.
And that's different with the mixing state. Mixing state can vary with for the same chemical composition. So internally mixed only says that you have several components in a single particle. Doesn't say anything about the mixing state.
Okay, sorry, I don't think I understand. But let me get to the Suzanne's point. So in our case, we assume internally mixing for here, and so okay, so I would say that size is actually more sensitive, but chemical composition do matter. I mean, it is matter, but size is more bigger component, like a bigger impact on GCM.
Yeah,
so
but to get the size right, you need to know the mixing.
Without the mixing state, you will never make it to 100 nanometers. Correct. You have to, the mixing state below 100 nanometer will define how many will cross the line and how fast.
I think we can talk about that. Yeah. Any other questions? Yeah.
So in the last plot you showed, can you, and do you plan to do a better job, including also all the semi?
Yes, not my job.
No.
There's one student, like a PhD student in Carnegie Mellon. He actually do the simulation with including all the effect. I mean, effect because. I mean, as you know, in real atmosphere, everything occurring at the same time, so it's not, you can distinguish. So, which is true. So, yeah, he's doing that simulation.
So, and many of these things are very, not very well known how they do it. So, my guess is that you have a huge error bar on your final results. So,
Yeah. I mean, of course, sometimes it's hard to estimate what error bar there, but I mean, for now, most of this study is based on modeling because it's hard to approach from the, observation. But there is some study coming, like they using satellite data. And they try to distinguish what's they are not distinct. They try, but it's not good yet. But hopefully, many years later, they can do better. But it's a pretty active study. They actually try to use the satellite data, try to come up with the forcing numbers.
I don't do any aerosols, but I'm interested in what do you think the uncertainties are for the emissions that you use?
That's a very good point.
Because nobody ever talks about that, and that's what I'm interested in.
No, so, it's very important. In fact, I cannot talk, I don't know how well I can explain for other species, but for dust parts, I was working on developing dust model as my first project. And for that case, depending on what emission you use or how you treat the size distribution, like emission size distribution, it has a totally opposite impact on GCM. So primary emission is very important, but the thing is the information or I can say there is less data available for global modeler to choose emission. But there's some people David Street, like there's some people they actually working on emission and they try to provide a better emission. But I can tell you like exact what's the uncertainty, like yeah. But that's very important.
That was a frightening slide at the A-Train meeting. Was a guy from ECMWF showed their aerosol assimilation. And they have 75 kilometer resolution winds, so they have nice fast winds. And they get lots of dust uplift. And he compared his dust predictions to satellites. There was nowhere near enough dust. And he had to quadruple the amount of dust that was getting lifted. So I mean, you know, with the GCM you don't have anything like that kind of wind speed.